So earlier in the unit, we talked about waves as being either mechanical waves or electromagnetic waves. And just as a reminder, mechanical waves were waves that needed a medium to be able to transfer their energy. Well, electromagnetic waves do not necessarily need a medium. Matter of fact, they can travel through empty space, so they do not require a medium. But an electromagnetic wave is a wave that's partially electric and partially magnetic, and it comes from the vibration or the movement of electrons. So let's talk about where electromagnetic waves originate. So here you have an atom, and right here would be an electron. It's just hanging out, not really doing anything, and then va-vam, here comes some energy right here. And the energy causes that electron to become excited. And so instead of being right here near the nucleus, it jumps a couple of energy levels. And so now it is way out here, farther from the nucleus, because all this energy was added to it. And so now we call it an excited electron. But then it doesn't stay there forever, because once the energy is no longer added, it's going to fall back down. So it's going to go from that excited state back down to its original state. And as it does that, it releases some of the energy that it absorbed. And sometimes it can release that energy in the form of visible light, which we can see, but sometimes it releases that energy in another form of light that we can't see, such as a radio wave or an X-ray. So electromagnetic waves are created when electrons move from one energy level to another and then back down again. And then they re-release that energy, usually in what we call a photon. And when they release that energy, it can be one of many types of energy. And all of these types of energy fall into what we call the electromagnetic spectrum. And they are all forms of light. Some we can see and some we can't. So these kinds of electromagnetic radiation are low frequency types of radiation, have very long wavelengths, and low energy. And then you follow the spectrum to this end. The types of electromagnetic radiation on this end are high frequency, short wavelength, and high energy. You can almost think that there's a dividing line kind of right about here. Anything below this line, from visible to radio, are usually types of energy that typically do not harm or do much to cells, living systems. They do some, obviously, because we know visible light can stimulate photosynthesis. So we know that it can stimulate some chemical changes. But the types of energy that are on this end of the spectrum have so much energy that they can not only excite cells or cause cellular changes, but they can do even more damage than the other cells. When you look at the types of radiation here, you probably recognize that a lot of them are familiar. Radio waves, microwaves, infrared. We get exposed to all of these kinds of radiation at some point in our life. And the ones that are on the far left part of the spectrum are ones that typically, when we're exposed to this type of radiation, do very little to our body, do very little to our cells. On the right side, the ones that are at the higher end, we have limited exposure to these because we know that these can cause damage to cells. So the gamma rays, very, very high energy, and so they have a very high frequency. So we definitely know about the electromagnetic spectrum. Down here, the visible spectrum, probably familiar with this, an acronym ROY-G-BIV, red, orange, yellow, green, blue, indigo, violet. Well, this spectrum down here follows the same pattern as the one above. The reds are going to be the ones that are the low frequency, long wavelength, and low energy. And then as you progress across, the purples and the violets are going to be the higher frequency colors of light. They'll have the shorter wavelengths, and they will be the higher energy colors. Just another way of looking at the same spectrum, This one kind of shows the wavelength and the frequency to give you a visual that the radio waves have a very long wavelength and a low frequency, whereas the gamma rays have a short wavelength and a high frequency. If we go to our first slide where we were able to look at the electron moving from one energy level to another, and as it fell back to its original energy level, it released energy. When it releases this energy, it releases it in the form of a photon. A photon is a massless bundle of radiation. And just because it says the word radiation doesn't always mean that it's harmful. Remember, radio waves are a type of radiation, and we're exposed to radio waves all the time. So a massless bundle of radiation is called a photon. And now we also have this information about the speed of light. 3 times 10 to the 8th meters per second, 300 million meters per second. And all of those different types of radiation, as I mentioned before, they're all types of electromagnetic radiation. And technically, they are all types of light. We just happen to be able to see only one small portion of that spectrum, the visible spectrum. But all of them are types of light. They all travel at the speed of light. Radio waves travel at 300 million meters per second. So do ultraviolet waves. So do microwaves. So does red light. So does green light. All forms of electromagnetic radiation, regardless of wavelength, regardless of frequency, they all travel the same speed through a vacuum. Now when they travel through different materials, because they have different wavelengths, they're going to behave a little differently. Materials that are transparent primarily let almost all the light pass through. If, however, light interacts with this material at an angle, it can still pass through, but it might change the path of the light. Such as when you shine a light through a window, if you shine it directly at the window, it'll pass through directly. But if you shine the light at an angle, some of that light might get reflected, some of it will pass through, and when it passes through, it might pass through at a different angle at which it came in. And you learned about that in a previous unit about refraction. So as the light passes through the material, the transparent material, it might refract or change its path. Opaque materials typically absorb most of the light, but they can also reflect some as well. So an opaque material is probably either going to absorb the light energy and probably convert it into thermal energy, or it can reflect that energy. So, speaking of reflection, when we look at an object and we see a particular color, the color we see is due to the wavelength that's reflected to our eyes. If it's a really short wavelength in the visible spectrum, then the object will appear bluish or purple. If it's a very long wavelength in the visible spectrum, then the object will appear red. And the reason why we see some of these different colors is because in our eyes, the back part of our eye is a surface called the retina. And the retina is loaded with specialized cells called rods and cones. The rods are primarily cells that are most active and most effective when the light is very dim. So basically your night vision is responding to the rods in your retinas. When there's not a lot of light available, such as at night, you tend to not see color. You tend to see more things in shades of gray, dark, light, that kind of stuff. So at night, your rods are helpful in helping you to detect different levels of brightness. But during the day, when you've got plenty of light around, your cones operate, and they help distinguish the different colors. And you have cells in your retina that are sensitive to red light, or the long wavelengths, to blue light, and to green light. These are the three primary colors of light. So when you see a particular color, these cells are being stimulated, and as they're being stimulated, that's the information that's sent to your brain. And so something that is pure red is primarily stimulating red cells or red cones in your retina. When you see something that's yellow, most likely it's stimulating your red cells and your green cells, and that combination of red and green stimulated cells produces a yellow color in our brain. So they release the signals, and that's what triggers us to see the various colors that we interpret. Someone that is colorblind typically has one, two, or maybe all of the types of cells that just either do not operate efficiently, or they're not even there. For example, somebody that might be red-green colorblind would have great difficulty distinguishing red and green objects from each other. To them, they might look the same color. So colorblindness would be a defection in the cones. The final thing to mention about color is right here at the bottom. If you were to equally mix red light, green light, and blue light, you get white light. White is not a true color. It's the mixture of all of the colors reflecting back to your eyes equally. So when something reflects red, green, and blue light equally, your eyes will sense that as being white. So white is not a true color. It's the combination of three colors put together. And the color black is also not a true color. Black is the absence of reflected light. When you look at an object and it appears black, it's because none of the colors, red, blue, or green, are being reflected back to your eyes. So your eyes are not getting stimulated because there are no frequencies being reflected back to your cones. So an object that is black because nothing's being reflected to your eyes. An object that is white because all of the colors are being reflected to your eyes. So black and white are not true colors the way that red, green, and blue are.